Welcome to the Yupp Master. Today we are going to deal the previous competitive examination problems in the chapter name of light. So we are going to take the different properties of light, that is refraction, reflection, total internal reflection and lateral displacement, and time taken by the light to travel the distance in a one denser medium. That is the case we are going to discuss. So I am going to convey about this narration of the topic. We are going to take the diagrams and we are going to take the animated pictures to solve the problems. Generally we are going to solve the problems in a direct method. So indifferently you are going to have that some approach, that is you are going to take the central theme of the problem. What we are taking, let's see, refraction of light. While you are solving that problems, just see that we would like to have the discussion with the diagram based concept. Then only we can learn more concept. It's very clear. Now what you have seen, yes. So this is the incidented light ray, very clear, and this is the normal, medium 1, medium 2. It is very clear. From this diagram, in how many ways that you can solve the problems? First thing, the incidented light is in the form of wave. You know very well about that. Light is traveling in the form of wave. All right. And it travels from one medium to another medium, and there exists a change in wavelength, change in the speed. It's very clear. And the frequency doesn't alter. That is very clear. Next, if you are taking that, if you are going to consider the previous concepts what you have learned in the lower classes, you know that wavelength, you can confirm that here you will talk about that V1, lambda 1 and nu, and we know very well V2, lambda 2 and nu dash. These are all discussed in detail. So from this picture what you can understood, the incidented light ray has been refracted and it bends towards the normal, no doubt at all. Medium 1 is the rarer medium. Medium 2 is the denser medium. It is very clear. And next you can take that point of contact, that normal. It is used to measure the angle of incidence and angle of refraction. Very clear. And you know very well about that mu 1, mu 2. Yes, mu 1 and mu 2. And this is a light wave. This is a light wave. No doubt at all. From one medium to another medium, there exists a change in its wavelength, and doesn't change that frequency, no doubt at all. Frequency means the number of oscillations made in 1 second regarding to that incidented light ray in the rarer medium. At the same time, the number of oscillations made in the medium 2, that is nothing but denser medium, they are going to be same. It has been shown. Very clear. So the change has been carried in terms of speed, not in terms of frequency. Very clear. Now you can take the ratio of refractive indices, that is mu 1 and mu 1 and mu 2. You will take that ratio of mu 1 and mu 2. It is very clear. You will confirm that it is the ratio C by V1, C by V2. Now at the same time, if you are going to take that, this is V2 by V1, V2 by V1, and you know very well about that. In the previous classes what you have learned, in case of waves, V is equal to nu lambda, very clear. V1 is equal to nu lambda 1, V2 is equal to nu lambda 2. So instead of that, can I write down nu lambda 2 by nu lambda 1? So finally what we have obtained, let's see. So this is mu 1 by mu 2 is equal to lambda 2 by lambda 1, very clear. At the same time, you can frame that relation among mu 1 and mu 2, that is equal to V2 by V1. This is also one relation. We know that. So it is evident, the diagram which gives the clear information, everything is identified, the change of speed related to the change of direction and that wavelength. If you are going to take that relations among mu 1, mu 2, V1, V2, mu 1, mu 2 and lambda 1, lambda 2, and all are clear. So let's go for the problems. It's very clear. Apart from that, we can have that problems. Let's see. Yes, very clear. So the problem has been related to previous one. If you know all the formulas and if you have been derived all the relations, they are very useful in the present problem. All right. Now we can look into the problem. Let's go for that. A light radiation of frequency nu in air enters into a glass slab, very clear. Then the frequency of wavelength and then the frequency, wavelength, velocity of the light radiation in the glass slab will be. Let's see that possibilities, what we are having that. It's very clear. Now, if you are going to take that, yeah, light enters from one medium to another medium, no doubt at all. Yeah, this is considered air medium, this is the glass medium. So we can take light is going to be entered, yes, it has been refracted, yeah, it's going to be identified. Yes, you can take that. This is, it has been taken. Yeah, you know very well about that. Mu 1, mu 2, V1, V2, and now it is very clear, you can approach. Light has been, this is the normal, it has been refracted. Now can we take that ratio of mu 1, yeah, mu 1 by mu 2 is equal to C by V1 whole upon C by V2. It is very clear. This is V2 by V1. Now you can take that. This is the first equation, let us assume. Now mu1 by mu2 is equal to V2 by V1. Now you can take V2 is equal to mu1 V1 by mu2, and you can know that V2 is equal to 1 into V1 by lambda 2. Very clear. Simply, in what way that does you can understood that matter? The speed of light in the second medium, the velocity of light also in the second medium, it travels in the straight line path. So the V2, it is going to be reduced 1 by, yes, thus you can write V2 is reduced by refractive index of the second medium. So easily you can write down that V2 is equal to 1 by mu2 times V1. So can you take the relation V1 and V2, which is greater? You know very well about that. In rarer medium, the speed of light is going to be high as compared to denser medium. So V2 is the speed of light in the denser medium. V1 is the speed of light in the rarer medium. From this expression, what you will confirm? V1 is greater than V2 or V2 is greater than V1? How you will decide that? Please, let's have a look. That is, you can take V1 is greater than, you will confirm that. As you have obtained that V2 value, it is going to be by reduced mu2 times, right? So you will confirm that this is the one relation, V1 is greater than V2. This is all right. Right. Let's go for this. V2 is equal to, we have obtained this one. Yes. Let's go for another one. Now you can go for another one, that is we can take, it's going to be erased due to the limited space, we can erase some part. Now you know very well that we can get the relation between these two things, V2 by V1, that is nu lambda and nu dash. In the first medium and second medium, there exists no change in the frequency. Yes, these are all equal. Now you can take that nu lambda 2, nu lambda 1. You can cancel. It's very clear. Therefore, mu1 by mu2 is equal to lambda 2 by lambda 1. Very clear. Now you can take that lambda 2 is equal to lambda 1 by mu2. So it is going to be 1, since mu1 is equal to 1, that is air, for air. Yes, you can write down easily, it's going to be 1. Now you have obtained that. Very clear. These are the fundamental relations. Yes. Why the frequency is not going to change means the change of frequency has not absorbed in case of denser medium. So the change might be carried in terms of the momentum. So it was carried in terms of change in velocity, change in speed. So that if you are going to have the deep discussion according to microscopic view and quantum mechanics, the change in momentum has takes place, but the frequency remains same, but the frequency is nothing but the number of oscillations made in 1 second. They are going to be very clear. Now have a look into that matter. First one, first option is the correct option as compared to remaining. What we have started with the diagram and we are taking that relations and we are concerning this. All these are very, very important. So this is correct, this is correct, this is also correct as per our discussion. Right, let's go for another one. Yeah, please take this problem individually. They have given the wavelength of light which is entered. Green light wavelength is 5460 angstrom units. This is given. Is incident on air glass interface. You can take that air glass interface. If the refractive index of the glass is 1.5, refractive index of glass is 1.5, then what they are asking, what is the wavelength of the light in that glass medium? Yeah, in the glass medium. They have given the C also. What they have given, let's see. Right. Now you can take that given data, that is, yeah, lambda air. Yeah, you will take that lambda 1, it's better. Lambda 1 is equal to 5600 angstrom units and mu 2 is equal to 1.5 and mu 1 is equal to 1, that is air, and they have given speed also 3 into 10 power 8 meter per second. But you need to calculate lambda 2, that is equal to question mark, just you can take this one. So you have finished that part 1, just you have been obtained all these given data. What the next? You can go for calculation part, that is lambda 2. By knowing the relation lambda 2, we can solve the problem, that is, yeah, lambda 2 is equal to, here we can write, yeah, you know that formula, that is lambda 2 is equal to lambda 1 by mu 2. Simply I can write lambda 2 is 1 by mu 2 times that of lambda 1. It's very clear. Now you can substitute that. Yes. Therefore, lambda 2 is equal to 5460 angstrom units by, what about 1.5? If you are going to make that simplification, 15, yeah, you can take that, yeah, and just you will get that 15 3 times 45, and then you will get that 96, 90, and yes, 40, yes, you will get that 60, yeah, 600, it is going to be 40 times. Finally you got that 3640 angstrom units. Let's check it. Yeah, first one is a correct option, Very simple problem, basic model problem, you will get this one, right. By knowing this, here we are going to ignore about that. This we have taken that mu1 is equal to 1, that is for air medium. Very clear. Now let's go for another problem. Please have a look. In the problem, we are going to solve the relative refractive index. What do you mean relative refractive index? The refractive index of the first medium with respect to the second medium, that is known as relative refractive index. So the term relativity, it is going to have that comparison with another one of the same kind. You know very well about that relative refractive index. In case of the refractive indices of a first medium and second medium, they have given the set of values. Let's see. You are going to deal that. Yeah, you have taken two different mediums, first one and second one. What happened? Let's see. Light has been incidented. Light has been incidented. It has been traveled from first one to second one. Let us assume. From the air we have been incidented the light rays and they have been traveled. Let's see, from air medium the light rays are entered into the denser medium. It's very clear. After that they are going to be refracted from denser medium 1 to the denser medium 2. Let's see, how do you know that? It's going to be known as, it's a refractive index. All these are identified as mu1 is equal to 1, mu2 is equal to 2, mu3 is equal to 1.5, and again it is mu4, that is. So this is the case with what we have taken. Light has been entered from one medium to another medium. After that it is continuing refraction. It is entered from second medium to third one, third medium to fourth one. So the refraction phenomena has been identified by the number of times, right. You can take that these two, first one, second one, you can calculate the refractive index, and second one and third one, you will calculate the refractive index of third medium with respect to the second medium. Relative refractive index, that means relative refractive index. Is it possible to calculate the refractive index of third medium with respect to the second medium? Again, refractive index of the fourth medium with respect to the third medium also is possible. So you know the phenomenon of relative refractive index of a medium. So when you are going to consider that relative means, you have to compare with another one. You have to take the consideration of the refractive index of another one which is originated from first medium to second medium. It's very clear. In that case, what we are going to take that, here we can, with respect to these two media, we are going to write down, that is mu2 by mu1, refractive index, relative refractive index, that's we are going to take that. So we can take, in case of these two, you will take that mu3 by mu2, relative refractive index, that is expressed, and this one is also air medium is there. You will take that. This is also expressed, that is mu4 by mu3. It has been identified as in the form of expression, that is equal to mu, we will take that mu 3 2. Sometimes you can write down 1 by mu 3 4 also. You should take the reciprocal. Generally, sometimes they are going to represent in reciprocal also. Is it possible? It is very clear, we are going to take that. What happened? The relative refractive index, when light enters from rarer medium to denser medium and light enters from denser medium to rarer medium, the refractive index of that second medium with respect to the first medium is changes from the original value. That is very clear. Let's see. For example, light enters from glass to water. The relative refractive index of that particular case has been identified, 1.2. Actually, the refractive index of that water medium is going to be known as 1.33. In that case, the relative refractive index of that water medium with respect to the glass has been less than that of original. That is the case we have to consider. Let's see in the problem. Yeah, it is very clear all about this relative refractive index concept. Yes, right. You can take that. This is also mu to 1. Yes, it's very clear. You may extend many objects, that we can take that, which are very transparent. They are the transparent materials to the light. So we cannot stop the light not to enter from one medium to another medium. It is going to be continuous process. It will enter. So multiple times does it takes that refraction. It is very clear. Let's go for the problems. Yes, the velocity of light in glass whose refractive index with respect to air is, this is the velocity of light in the glass material, and they have given that. Same, from that glass to, it has been entered into one type of liquid. They are not mentioning that name, liquid. The speed of light in that liquid is 2.5 into 10 to the power of 8 meter. Very clear. The refractive index of liquid with respect to air. The refractive index of liquid with respect to the air, that is called relative refractive index. Yes, very clear. Now you can get this data. These type of problems are solved with the previous discussion what we are having. Yes, very clear. So simple, they have taken, this is glass and this is water. Light enters from glass to water. So you know very well about refractive index of glass with respect to the air they have given. And you are supposed to find out that refractive index of water with respect liquid, refractive index of liquid with respect to the air, you have to find out that. This is the air. Very clear. So let's go for the problem. I hope so. It is easy for you after the discussion, after the explanation of all the points related to relative refractive index. Let's solve the problem. We will accept that. Yes, we can take that. Glass, it's a one case. We will take that glass material. Light enters from glass to liquid. That is mu g. Refractive index of glass is 1.5. That is you have to take that. Refractive index of glass with respect to the air is 1.5. That is very clear. Next, you know very well V glass, Vg, the velocity of glass Vg, that is 2 into 10 to the power of 8 meter per second. Now you can take that. They have given V liquid. This is Vg means, you can take it's very clear. this is VL, that is equal to 2 into 10 to the power of 8 meter per second. Now you are going to find out that mu refractive index of liquid with respect to the air. With respect to the air. Yeah, you will take that. This is air. So, question mark. That is the relative refractive index. They are going to solve the problem mu, L and A. Can we approach with the knowing formulas? Very clear. Now we can use this space. Yeah, you know very well about that. Mu G by mu G air, it is equal to mu G by mu A. We are going to take that ratio of the two relative refractive indices, that is whole upon mu L by mu A. Yeah, we are going to cancel the term, that is equal to mu G by mu L. Yes. So it is equal to C by Vg. Simply we are going to take that C by Vg whole upon C by Va. Sorry. Yes, VL. Now we are going to take that cancellation. Finally, VL by Vg. Please have a look. This is the case. We are going to take that. Now we will erase this. What we are using? Yes, we have obtained that final expression, that is mu G air by mu L air, that is equal to VL by Vg. They have given the value of that mu G, they have given the value. Very clear. Now we can take that 1.5 by mu L A, 1.5 by mu L by A, that is equal to 2.5 into 10 power 8 we will take that. Yeah, meter per second and 2 into 10 power 8 meter per second. It's very clear. Now let's go for the cancellation, right? Easily you will find out this parameter. If you are going to take that cross multiplication also, easily you will find out that. Therefore, yeah, mu 1 upon mu L A is equal to 2.5 by 1.5 into 2, that is 25 by 30. So that implies mu L into A. Please have a look. The calculation is given very detailedly, is equal to 30 by 25. Now we can take that cancellation, 5 5s and 5 6, that is 6 by 5. Now you can take that 1.2. Yes, what we have obtained that final result. This is the final calculation. that is the refractive index of liquid with respect to the air, that is mu L. It is nothing but mu L. Yes. What we have obtained the answer, let us see. Yeah, this is that 1.2. Second option is the correct one, 1.2. Very clear. If you are going to observe, we have approached that solvation method step by step. First one, second one. First of all, you need to understand that problem, what they have given, what is your aim, how it is related to the relative refractive index concept. Very clear. So it is related to the relative refractive index concept what we have discussed in the previous one, that you can easily substitute and easily convert and get the necessary calculations and the cancellations, and you can go for that some multiplications and divisions which are done by you very quickly. Easily you can do that. So final answer is 1.2. Generally the refractive index of liquid, so let us take that water. How do you know it is water? With the help of the speed. The liquid is nothing but water. What is the refractive index of the water generally? It's going to be 1.33. What we have obtained, that is 1.2. What we have taken, the relative refractive index concept. We have calculated that relative refractive index of that liquid and air. Very clear. Now let us go for another one. It is useful. While you are going to look into that one, please take that one screenshot. It is useful how we are going to convert it. Yeah. Let us go for another one. Please have a look. Yeah, this is a one picture what we are going to narrate that. I hope so. This is related to the phenomena of refraction. Let's see. Yeah, the person, that boy is going to observe that the fish is actually the presence of that fish is going to be here only. What happened due to the refraction of the light rays? Yeah, the light rays are entered and again they are going to be approached from that surface, from the lower surface. So there is just a refraction. It is going to be raised, the image of the fish. What is the actual presence? Here. Actual presence is here. But it is going to be raised. So it is going to be raised. This is virtual. It is not real. So it has been appeared, it has been raised to a part of some distance, like that. So that this is the apparent depth, this is the real depth. This is the real depth and apparent depth. This is a very simple concept, you can know that. We can frame the relation between real depth and apparent depth by using the formulas, that is mu is equal to real depth by apparent depth, and also you can go for that apparent depth is less than that of real depth when it has been observed from the rarer medium. What you can take that converse, if suppose that boy is in the deep water, he has been observed the flying bird. At that time the apparent depth is greater than that of real. Apparent distance, we are going to take that apparent distance is going to be greater than that of real. It's going to be, he was having the observation from this medium, from this one, he was going to be observer. He was going to look a bird which is going to be flying. So in that case, what happened? D apparent is greater than D real. That is the case we have to understand. They may frame the problems based on different cases. Observer, suppose a swimmer, he has seen that other than 90 in that view, the flying bird is going to be appeared, what actual presence is there greater than that of actual presence. That is, the apparent depth is going to be, the apparent distance is going to be greater than that of real depth. It is very clear, you have to know that concept, and they will frame that theoretical questions also based on this phenomena. Yes, have a look and observe this one, very clear. Now let us go for the problems based on this concept. If you are taking that coin also, yeah, a bubble in the glass slab, when it was viewed from one side it appears 5 centimeter and 2 centimeter from other side, then thickness of the slab, right. So you can take that the total apparent distance is going to be 5 plus 2 centimeter, that is 7 centimeter, very clear. Now you are finding that D apparent, you can take this one, this is equal to 7 centimeter, no doubt at all. Now if you are going to have the relation mu is equal to real depth by apparent depth, that is 1.5 is equal to 7 by, what they have given, just you have to write down. We don't know the thickness, it is nothing but, the thickness is nothing but actual distance. This is the glass, it has been viewed from one side, it has been viewed from another side. This is of case that what you are going to know that this is the actual depth, this is the T. Let us assume T be that. So the T is equal to 7. If you are going to take that, you can easily multiply. This is the case what it has been viewed. You have to take that. This is the one apparent depth. This is that. We are going to take the total apparent distance, and it is going to be thickness. It is the real depth. Very easily you can solve the problem. You can take that 1.5 into 7, that is equal to T. You will get that 7 plus 3.5, that is 10.5. Yes, you can take that multiplication, that is 3. Very clear. I will take that. Now please have a look, answer, that is third one is the correct answer, very clear. Shall we go for another problem based on this model? Yes, it's very clear. Similar kind, but they have given that some another model problem, but related to the concept. A mark at the bottom of a liquid appears to rise by 0.1 meter. 0.1 meter. The depth of liquid is 1 meter. The refractive index of the liquid is, you have to find out that. Let's see that concept, what they have given. So you have to use that formula. Apparent shift is equal to T into 1 minus mu. So this is D apparent, that is equal to T into 1 minus 1.5, you will take that mu only, but they have given that 0.1 meter into 1 meter thickness into 1 minus 1 by mu. You will take that. You will take this all calculations. Easily you will find out that mu is equal to 10 by 9. I hope so. Yeah, you are getting that answer after the calculation. All of you, it's better to have that, look into that matter, how you are having that joyfulness while watching these videos. I think you are all getting that knowledge. At the same time, you are having the capability to do the problems. Please convey to the more number of peoples regarding to this App Master classes. Thank you very much.